ECC stands for Error Correcting Code, and you've probably already heard of this before in the context of computer memory. But how exactly is it done? Let's find out. I'm Mr. Lustig, and as you can see, I'm a stick. I never correct my code.
What's that supposed to mean?
It means I never correct my scripts, so yeah, don't trust anything I say.
Who the would trust a weird stick like you on YouTube?
Thanks for the vote of confidence. First, why do we even need ECC? Well, Earth is constantly bombarded with cosmic rays. But the kind that generates a shower of particles when entering Earth's atmosphere, not the kind that give you stretchy limbs.
My wife would really enjoy that, if you know what I mean.
And they will definitely not give you a nice butt. Cosmic rays are high-energy particles, which can come from the sun's solar winds, but the highest energy cosmic rays come from remnants of supernovae and supermassive black holes.
Whoa, he wasn't lying in the title.
The shower of particles from cosmic rays can also generate charged particles, and computer memory basically boils down to storing a charge in a transistor. So if a charged particle interacts with the charge stored in said transistor in just the right way, it could change its value, causing a bit flip, or a 1 turning into a 0, or vice versa. CERN estimates that every second a non-charged particle created from a cosmic ray hitting our atmosphere passes through your head. So we get quite a few hits from dying stars and black holes. One study estimates that a 4GB DIMM of RAM has a 96% chance of experiencing a bit flip within 3 days.
Well, I don't want no bit flips. What do I do now?
As the name implies, error correcting code will correct a bit flip. There are many types of ECC, but the most common one is Hamming code. Richard Hamming invented the code after a program that he left running over the weekend in 1947 at Bell Labs had an error early in the process, which caused the calculation to be wrong. He reasoned that if a computer can detect an error, it can also repair it. The solution he came up with, which he published in 1950, has a lot of math behind it.
Please don't start talking math.
But don't worry, there's a much easier way to visualize the method. What the Hamming code does is add a number of parity bits to the amount of data bits you want to protect. The number of data bits that can be used is 2 to the power of the number of parity bits minus the number of parity bits minus 1. So it gets more efficient the more data bits you use. Now, each parity bit is just going to say whether the number of ones for the bits over which it is used is odd or even. The magic of this method is interleaving the parity bits with the data bits, so that the new stream of bits contains a parity bit in each power of 2 locations. Each parity bit will represent the odd or even number of ones in the new stream of bits, corresponding to whether the data bits positions in binary have a 1 in the parity bit positions.
Say what?
So, for example, 6 in binary is 110, so the data bit in position 6 will be used in the calculation of the second and third parity bits. The parity bits themselves are not used for any calculations. Seeing this for the Hamming code on 4 data bits is going to help. According to the formula, there are 3 parity bits and 4 data bits. Looking at which data bits are used in the calculations, you can see a pattern emerge. Anyone who's ever made a binary table will understand it immediately. It's basically counting in binary. The parity bit calculations correspond to the binary code of the position. So now, when we receive a stream of bits, we will calculate each parity bit, and if any of them are wrong, the binary representation of the failures will tell us which bit got flipped. Suppose we get a bit flip in data bit 6. Then the parity bit calculations will be different for the second and third bits. Bit 1 is unaffected because it doesn't get used in the calculation. So we get 110, or 6 in binary. So now we know that we need to correct bit 6, or flip it. If just one parity bit is wrong, then we know that it was actually the parity bit itself that got flipped. The drawback of the Hamming code is that 2-bit flips are indistinguishable from 1-bit flip. But if we add another parity bit over the whole stream of bits, we can detect 2-bit errors and correct single-bit errors. Here's how. If all bits are 0, then there's no error. If all bits except the global parity bit are 0, and the parity bit is 1, then we had a bit flip on the global parity bit. If the global parity bit is correct and the Hamming parity bits are wrong, then we have a double bit flip. And if the global parity bit is wrong and the Hamming parity bits are wrong, then we have a correctable single-bit error. All these calculations do affect memory performance, so ECC memories are generally used in servers, especially for financial applications or other places where retransmission would take a long time, like distant satellites. Consumer GPUs with ray tracing capabilities have started using ECC VRAM because small errors in ray tracing can have large visible end results. There are more mathy ways for implementing ECC. Some can correct more than 1 bit, but I don't want to spend time understanding that. I have better things to do with my life.
Like masturbating.
Well... And if you like this video, just give it a thumbs down. I'll show it in the title. And if you bit flip your way to the subscribe button, I promise it will correct itself.
I don't understand how we can turn something cool like black holes into something so boring like the video you just watched. If you want to see more boring stuff, click one of these videos. I wouldn't.